How does a cup of coffee in space connect with a floating sewing needle? Whoops, it sank. Well, that connects too. Hi, I'm Dave Dooling, and in this session of Virtual Rocketeer Academy, we'll look at surface tension, an unusual, important bit of physics that we see in water and other chemicals. You'll need these items: wax paper, a small bowl, a sewing needle, a pin, dish detergent, a plastic water bottle, a food storage bag, paper towels, an eyedropper, a straw. Lay out a sheet of wax paper. Squeeze a few drops of water onto it. Notice how it stands up in little beads? That's caused by surface tension. The water molecules pull on each other and keep the droplet from spreading out, and they are repelled by the wax in the paper. Let's try another experiment. Fill the bowl with water and gently place a thin sewing needle on the surface. It floats, even though metal weighs more than water. Why? Again, the water molecules pull on each other. The weight of the needle is not enough to break what appears to be a thin skin that keeps the needle afloat, or lets bugs walk on water. Breaking the tension is easy. Dip the head of the pin in the soap and then touch to the drop on the wax paper, and repeat with the water that floats the needle. Suddenly, the drop spreads out and the needle sinks. In fact, surface tension seems to shrink away from the soap. To understand what's happening, we need to dive into the water and to the level of molecules. Water is made of 3 atoms, 1 oxygen holding 2 hydrogen. But oxygen holds the hydrogen in an odd way. Rather than sitting at opposite sides of the oxygen, the hydrogen atoms are at an angle of 105 degrees because of how electrons arrange themselves at the outer edges of the oxygen atom. This gives water a slight electrostatic charge, like rubbing a balloon on your hair to make it stand up. Since opposites attract, the positive hydrogen sides of one water molecule are drawn to the exposed negative oxygen side of another water molecule. These are hydrogen bonds. We see its effects in 3 forms of water: ice, liquid, and steam. In room temperature water for our experiments, the bonds are strong enough to keep the molecules from escaping and form the skin that we call surface tension. It makes the water form a drop until it's too heavy and makes water climb the inside of a straw, which we call capillarity. Surfactants, surface active agents, like soap, break hydrogen bonds. That makes it easier for soapy water to clean dishes. This also keeps water from evaporating in a flash. Raise water's temperature and the energy of motion gets stronger. Hit 100 degrees and the molecules are moving fast enough to break free, turning from liquid to gas. But lower the temperature and something weird happens. As water cools, molecular motion slows. The water volume gets smaller until the energy of motion is only as strong as the hydrogen bonds. Water reaches its smallest volume at about 4 degrees above zero, and then it expands. The positive hydrogen in one molecule is drawn to the negative oxygen on the next, and the 105-degree angle between hydrogen atoms is close enough to the tetrahedron's angle of 109.5 degrees that hydrogen fixes the water molecules into a crystalline lattice and gives snowflakes their hexagonal shape. Molecules still vibrate but are locked in place. Water has become ice. The molecules take more volume and the density of ice is lower than that of liquid water. So, ice floats, which is good. Otherwise, it would sink and the oceans would freeze from the bottom up and never thaw. It also means that anything holding water can rupture without a little room to expand. It can even crack rocks and roads. Try it with a water bottle in a freezer. Use a storage bag to avoid making a mess. To review quickly, atoms in a water molecule are slightly skewed, creating a modest positive-negative attraction between molecules. This keeps liquid water liquid unless it's hot enough to break the bonds and boil, or cold enough to become ice. Astronauts playing with water show the connection to space research. Surface tension keeps water drops from dispersing. Drops don't pull apart, and you can even inject bubbles of air. Surface tension has been at the center of dozens of space experiments. With gravity's effects removed, cold doesn't sink, and warm doesn't rise. Surface tension effects stand out. This lets scientists study the role of hydrogen bonds in chemistry and improve those processes on Earth. And some rockets have screens that use capillarity to keep fuel near the drain, kind of like rain on a window screen. Oh, and the coffee in space? Astronaut Don Pettit came up with the design in 2008. Tired of drinking from a pouch, he combined the capillarity effect and a sheet of plastic to make a zero-G coffee mug. So the next time you see a blob of water standing on a windshield or ice cracking a bottle open, think about work on International Space Station. Thanks for watching, and stay tuned for more Virtual Rocketeer Academy episodes.